Hello everyone, welcome to this video. I am Prasanna Venkatesan. Today I am going to teach you on the most important concepts in microprocessor architecture, pipelining. In fact, pipelining is single-handedly the biggest reason why processors have become so fast over the years. If you look at your own experience, computers keep getting faster every year. But interestingly, neither clock frequency nor data bus size has increased significantly in recent years. So, the question is, what is really making processor faster? The answer is pipelining. Why to study this pipelining? Tomorrow, if you sit in an interview and someone asks, give me techniques to make a processor faster, you should immediately think of increasing data bus width, increasing clock frequency, and of course, the pipelining. And among these, pipelining is the most powerful and scalable technique. Let us start our discussion on classical ways to increase the speed. First, increasing the data bus width. If a processor has 8-bit data bus, it can transfer 8 bits at a time. If it has a 16-bit data bus, obviously it can transfer 16 bits of data at a time. So clearly, a wider data bus means fewer cycles, faster execution, but this approach peaked long ago. Pentium 1, released in 1993, already had a 64-bit data bus. Even today, most processors still uses a 64-bit data bus. So this method has physically and practically limits. Next, increasing the clock frequency. Earlier processors worked at 3 MHz, 5 MHz, 10 MHz, and the modern processors works at 3.2 GHz, 3.4 GHz, 3.6 GHz. Yes, this made processor faster, but here the key observation is clock frequencies has barely increased in last 15 to 20 years. Thermal limits, power consumption and heat dissipation prevents unlimited frequency scaling. So what is left? Pipelining. Despite these limitations, processors keep getting faster. Why? Because of pipelining. And today I will explain pipelining starting from the first processor that introduced it, that is the 8086 processor, and then I will connect it to modern processors. To understand the pipelining, let us compare a non-pipelined processor 8085 microprocessor with a pipeline processor 8086 microprocessor. We give both the processors the same program, the same number of instructions, and we compare the execution time. How a non-pipeline processor works, that is the 8085 microprocessor. Let us assume we have a program with 5 instructions. Remember, instructions are stored in memory, not inside the processor. Every instruction, the processor must fetch the instruction from the memory. So from the memory it has to fetch. After it is being fetched, it is decoded, it decodes it, and after which it will execute. In 8085, first instruction is fetched, then it is executed. Only after execution is complete, the next instruction is fetched. So the sequence look like fetch, execute, as shown here. After some times, all 5 instructions are completed. This is a serial. one thing at a time approach. Now let us discuss about how the pipelining happens in 8086 microprocessor. In 8086 we have two-stage pipeline. We have two-stage pipeline. Here the key realization Intel engineers made is when an instruction is being executed inside the processor, the buses are completely free. Isn't it? So the question is, why waste that time? There comes an idea that is nothing but of the pipelining idea. While the processor is executing the current instruction, at the same time the bus fetches the next instruction from the memory. So execution happens inside the processor. Fetch happens using the buses. Both occurs simultaneously. Resulting execution flow as instruction 1 execute, instruction 2 fetched, instruction 2 execute, instruction 3 fetched, and instruction 3 fetched executes, instruction 4 is being fetched. So after the first instruction, the processor is continuously executing without waiting. This is why execution time is drastically reduced. The formal definition for pipelining is the process of fetching the next instruction while executing the current instruction. Say it again. Fetching next while executing current instruction. Why 8085 could not pipeline? 8085 architecture was a single functional unit could do only one task at a time. Whereas 8086 architecture is different. It is being divided into two independent units, one for fetching instruction, one for execution. Because these units work simultaneously, pipelining becomes possible. Let us now discuss about the superscalar pipelining. Processors do not stop with one pipelining. It has two pipelines running in parallel. This is called superscalar pipelining. So, if we have 5 stages and 2 pipelines, then 10 instructions are being processed simultaneously. Instructions are distributed alternatively to maintain program order. The extreme pipelining is in Pentium 4. The Pentium 4 NetBurst architecture took this idea to the extreme. It has 4 parallel pipelines. Each 20 pipeline has 20 stages. That means 4 into 20. 80 instructions are in a program that are being progressing at the same time. Compare that to the 8085 processor. The 8085 processor, one instruction is being taken at a time. In 8086, only 2 instructions are being taken at a time. This is why performance increased dramatically over decades, and the pipelining and multi-core processors evolved. Later, this idea evolved further into dual-core, quad-core, hexa-core, octo-core processors. Each core can be thought of as a separate pipeline with multiple internal stages. This is how modern processor achieves massive parallelism. Now let us discuss about the drawbacks of pipelining. Pipelining is powerful but not perfect. The major disadvantage of pipelining is data dependency. If instruction 2 depends on the result of instruction 1, then instruction 2 cannot proceed until instruction 1 finishes. This problem is handled by compiler optimization, no op insertion, no operation insertion, instruction reordering. And the next drawback is branch problem, a very important problem. So pipelining assumes that the instruction executes sequentially, but real program contains if statement, loops in the program. And also there may be some functional calls. When a branch instruction occurs, the processor may have already fetched the wrong instruction. That instruction must be discarded. This is called branch problem or pipeline flush, or we will be calling it as pipeline failure. So the pipeline penalty is of, if we are having 2-stage pipeline, 1 instruction is wasted. 3-stage pipeline means 2 instructions are wasted. 20-stage pipeline means up to 19 instructions are wasted. As pipeline depth increases, branch penalty increases. The solution for this branching problem is branch prediction. The modern processors uses branch prediction algorithms. Pentium introduced branch target buffer, history-based prediction. The processor predicts almost whether a branch will be taken or not based on the past behavior. The accuracy of this algorithm is 98 to 99%. This makes deep pipelining practical. So coming to the end of the lecture, let me summarize the things. In this video lecture, we have seen the pipelining overlaps instruction execution. It dramatically improves performance. It is introduced first in 8086, evolved into multi-stage pipeline, superscalar processor, multi-core architecture. The main drawback in pipelining is data dependency, branching. Modern CPUs solve these using prediction algorithms. So these things we have seen in this lecture video. I hope this lecture gave you a clear and complete understanding of pipelining from 8086 all the way to modern processors. Thank you for watching.